All right, chemistry, this is part 2 of your video lecture on section 2, radioactive decay. The last lecture, we covered these first 3 objectives. This lecture, we're going to finish up by allowing you to define and relate the terms decay series, parent nuclide, and daughter nuclide. And lastly, explain how artificial radioactive nuclides are made and discuss their significance. All right, now we're going to have to skip forward to where we left off. All right. Half-life. Let's start with the definition. Half-life, also represented as lowercase t subscript 1/2, is the time required for half of the atoms of a radioactive nuclide to decay. Half of them. Each radioactive nuclide has its own half-life. Every single type has its own half-life. More stable nuclides decay slowly and have longer half-lives. The other half of that is less stable nuclides decay much more quickly and have shorter half-lives.
Radioactive atoms are unstable. They will decay into a more stable atom by giving off some kind of particle or ray. Any unstable atom has a random chance of decaying in a certain period of time. In this simulation, the balls represent atoms. Each red ball has a 50-50 chance of decaying into a blue ball as 10 seconds go by. Let's stop the clock and graph the results. We started when the stopwatch read 0. At that time, there were 16 red balls. After 10 seconds, 8 red balls remained. Let's continue. The decays are happening less frequently because there are fewer radioactive atoms left to decay. 4 more radioactive atoms have now turned into a non-radioactive form. Another 2 become non-radioactive. In each 10-second interval or half-life, half of the total remaining unstable atoms decay. In the real world, atomic half-lives can range from a fraction of a second to 1,000,000 years or more.
All right, here is that same graph that we just saw described. We're looking at potassium-40 and its half-life. So we have some newly formed rock. It has a whole bunch of potassium-40 isotope in it. Yes, we don't have to understand geology just to assume that we have potassium-40 present in this rock, but potassium-40 has a particular half-life. Now, for potassium-40, it's very stable, so the half-life is very, very long. But we start with an original amount of potassium-40, and what we're representing here is the ratio of potassium-40, remaining potassium-40 to the original potassium-40. That's labeled here on the y-axis. And so we have 1-to-1. We have the exact same number of remaining potassium-40 as we had original potassium-40. So it's a 1-to-1. Now, the half-life here is stated as 1.3 billion years. So one half-life is 1.3 billion years. So if we allow 1.3 billion years to elapse, half of this potassium-40 will have been turned into something else. It will have radioactively decayed. So at 1.3 billion years, the half-life for potassium-40 will be at a 1/2 amount. Okay, the ratio of remaining to original potassium-40 is 1-to-2. If we allow a second half-life to elapse, okay, another 1.3 billion years, we will have allowed a total of 2.6 billion years to elapse. Half of that potassium-40 will decay and turn into something else. And so the ratio then of remaining potassium to original potassium will be this 1-to-4 we see on the y-axis, represented by the 2 half-life value on the x-axis. Once we get to 3 half-lives, which is in this case 3.9 billion years, we're down to 1-to-8. And after 4 half-lives, we're down to 1-to-16 in terms of that ratio of remaining potassium-40 to original potassium-40. I do want to point out this relationship. 1 half-life, okay, is 1-to-2. We have half of the original amount. When we go to 2 half-lives, we're 1/4. 3 half-lives, 1/8. And then for half-lives, we are at 1/16. And so I hope you see the exponential relationship between each of these half-lives. Okay? So we're actually going to have an inverse square of our original amount, where how many times we're squaring this original number is the number of half-lives that we have. Moving on to rate of decay. When we look at rate of decay, we have a particular isotope. We're going to measure it however we deem necessary. In this case, we have milligrams over millions and millions of years. This can, like the video said earlier, this can range from milliseconds, absolute fractions of a second, and it, but with other isotopes, this could take billions and billions and billions of years. The reason I wanted to include this particular chart is to contrast this with the potassium-40 that we saw with something completely different. It has a half-life on a completely different scale. Now, if we were to go through and to count each time half of these black dots turned into gray dots, every time it was 1/2, that would be a half-life. Every time another half of all of these black dots turned into gray dots, that would be a second half-life, and on and on and on and on. But notice, regardless of the element, regardless of the half-life, we always have the same shape of graph. Notice how this line is always asymptotal. Okay, it's always asymptotal. If you're always taking half of your remaining elements and turning them into something else, you're never going to reach 0. You're simply going to have a smaller and smaller fraction. So these are some common half-lives of some radioactive isotopes. We have carbon-14, iodine-131, potassium-40, radon-222, radium-226, thorium-230, thorium-234, uranium-235, uranium-238, and plutonium-239. These are some common radioactive isotopes that you may hear from time to time in the news, nuclear chemistry, physics, things like that. And these are their associated half-lives. Notice the massive variation in these half-lives. We have over here a 7.04 times 10 to the 8th years, okay, or in the millions of years. But then we have 3.82 days for radon-22. These half-lives vary radically. But notice each time one of these isotopes decay, they turn into some other element. Notice the carbon-14 becomes nitrogen-14. Iodine-131 becomes xenon-131. Potassium-40 becomes argon-40. Now here we get a little bit interesting. We have radon-222 becomes polonium-218. Radium-226 becomes radon-222. And this will lead us into a future topic, which is reaction propagation, but that'll come at another time. But please refer to this data table in the future. Now it's time for some sample problems. So we have phosphorus-32, and it has a half-life of 14.3 days. How many milligrams of phosphorus-32 remain after 57.2 days if you were to start with 4 milligrams of that isotope? All right. So let's identify what we start with. The original mass of phosphorus-32 is 4.0 milligrams. We are also told the half-life of phosphorus-32 as 14.3 days. We were also given the amount of time elapsed. Okay, we were asked how much is going to decay in 57.2 days. What we're trying to establish is the mass of the phosphorus-32 that remains after that time. So in order to solve this, we're going to take the number of half-lives. Okay, the number of half-lives. We're going to see that one half-life is 14.3 days, and we're going to use that as a conversion factor. We're going to use that as a conversion factor. So we're going to have time elapsed in days, which is 57.2 days. We're going to use the one half-life is equal to 14.3 days as a statement of equality to create our conversion factor. Okay, so we're going to have we're gonna have the number of half-lives present, and so the amount of phosphorus 32 remaining is going to be the original amount of phosphorus, and we are going to multiply that amount by 1/2 for each and every half-life that we have. So what is it going to look like? The number of half-lives equals 52.7 days multiplied, converted to half-lives using the statement of equality that we identified earlier. This is going to give us 4 half-lives. I believe this is actually a typo. This should be 57.2. Anywho, this is going to give us 4 half-lives. It should equal 4 half-lives. And so if we're starting with 4.0 milligrams, we have 4 half-lives. And so for each one of these half-lives, we're multiplying the total amount present by 1/2. So we're going to multiply 1/2 4 times. 4 times we're going to multiply by 1/2. Now, you can consolidate this 2 times 2 times 2 times 2, so that would be 1/8. You can simplify this by writing 4.0 milligrams multiplied by 1/8. That's completely acceptable. I wanted to write this out so you make the connection between the number of half-lives, and a half-life is, in fact, half of the total amount of the isotope. So our final answer is going to be reported with 2 significant figures because we see 4.0 milligrams is 2 significant figures. We have 0.25 milligrams will remain after 57.2 days. Now let's move on to Decay Series. A decay series is a series of radioactive nuclides produced by successive radioactive decay until a stable nuclide is reached. What we mean by successive radioactive decay, we mean it's a stage-based or phase-based radioactive decay. It happens in a series. You have one nuclear decay happens, and then the result of that nuclear decay decays again, and then yet again until that stable nuclide is reached. Why will something stop decaying? Because it's finally stable. So the heaviest nuclide of each decay series is called the parent nuclide. The thing that you start with at the very beginning, meaning the heaviest nuclide that you have that starts the whole thing, is called the parent nuclide. The nuclides produced by the decay of the parent nuclides are called daughter nuclides. Now, you're going to have many daughter nuclides for most decay series. So let's look at an example. We have the decay series for uranium-238. So we are going to start with uranium-238, and each time we are going to emit some sort of nuclear radiation. We're going to decay until that what was uranium-238 finds a more stable form. Now it's going to decay, and then it's going to emit a certain amount of charge until we get to a stable form, and then that will decay. Then we have a new parent nuclide that will decay, yielding a daughter nuclide, yielding another daughter nuclide, and again and again and again and again. And we have this successive series of radioactive decay.
Radioactive nuclei undergo a set of transformations until they decay into stable nuclei. Uranium-238, for instance, decays to lead-206 after many steps. The first step in the uranium decay series is an alpha decay. The alpha decay causes the atomic number to decrease by 2 and the atomic mass to decrease by 4, producing thorium-234. 2 beta decays cause the atomic number to increase by 2, producing uranium-234. Several alpha decays lead to an interesting part of the decay series. When the nucleus has decayed to 218/84 polonium, it has 2 possible pathways for further decay. Several of the other daughter nuclei also have more than one decay path. All of the remaining decay pathways, however, lead to lead-206. Because lead-206 is a stable nucleus, this is the end of the series.
And we're going to finish up with artificial transmutation. Remember, transmutation refers to the change in identity of a particular element. Now, back in the olden days, this was associated with alchemy, trying to turn lead into gold. right? Changing the identity of the element. But here we're talking about artificial transmutation. If you need to understand when this would happen, just think, hadron collider, okay? Particle accelerators. These types of things happen artificially. They're man-made in order to try to study the nature of the universe, physics studies, all that fancy-dancy stuff. Artificial radioactive nuclides are radioactive nuclides not found naturally on Earth. They are made by artificial transmutation, or bombardment of nuclei with charged or uncharged particles. For example, in those particle accelerators. Transuranium elements are elements with more than 92 protons. Remember, 92 protons is the point on the periodic table where we are going to find uranium. So transuranium elements are elements past that have gone larger or through uranium. Artificial transmutations are used to produce the transuranium elements. So when you look at the periodic table and you see those elements that are that have atomic numbers larger than 92, like neptunium, plutonium, americium, and on and on and on, these things are going to be made artificially. They are not going to occur naturally on the Earth. All right, chemistry, that concludes the lecture for this section. I will see you next period.